Hey everyone, welcome back to my channel. Today I will be discussing the derivative of the function f of x equals x factorial. So I've seen a lot of videos on YouTube with the same subject where they use the gamma function, which is the real extension of the factorial function, as it's generally defined for integers. But today we will discuss d of x factorial over dx, or f prime of x here, without using the gamma function at all, and only focusing on my favorite thing in math, recursion, or the recursive rules that define factorial. So we know f of 3 is 3 times 2 times 1, f of 5 is 5 times 4 times, then 3 times 2 times 1. I'll just go all the way to 1 and denote the general idea with n, that f of n can be rewritten as n times n minus 1 factorial. Now what we want to do is we want to use this recursive nature of the factorial to define the function recursively itself. So what that would look like is we would have f of x, and that's just equal to x. And since we see n minus 1 factorial is just f of x minus 1, because f of x is x factorial, we can just write times f of x minus 1 over here. Base case f of 0 equals 1, but you'll see why that's not quite relevant for the general form. Because although you need a continuously differentiable function to find the general form for all real x, what the equation we'll find is corresponding to the real extension of the derivative of the gamma function, which is just the gamma times digamma of x plus 1. So here we have the product rule. If you have g of x, u times v, g prime of x is u of v dash plus u dash v. We'll use this to find our f prime of x here. So that would be derivative of x, which is 1 times f of x minus 1, plus derivative of f of x minus 1 times x. So that would be x times f prime of x minus 1. Could do better with the spacing. Rewrite that. F prime of x is equal to f of x minus 1 plus x times f prime x minus 1. Much more readable. Now, what we're going to do to this equation is we want to divide the left-hand side and the right-hand side by f of x itself. And why do we want to make the substitute or this manipulation? Well, it'll be clear in the next few steps. So we want to divide the left-hand side and the right-hand side by f of x. This yields f prime of x divided by f of x is equal to f of x minus 1 divided by f of x plus, we can write x, this will not fit over here, but we will make it f of prime of x minus 1 over f of x and now we'll replace f of x from the original definition to be x times f of x minus 1. So that would yield f of x minus 1 divided by x times f of x minus 1. We do that to the other term as well, because division is distributive. So x times f prime of x minus 1 divided by x times f of x minus 1. And we notice something interesting. The f of x minus 1 from the first term cancels out with each other in the numerator and denominator, and then the x in the numerator and denominator of the second term, they cancel out with each other. This gives us a simplified expression for f prime of x divided by f of x, which is equal to, let's simplify this again for visual clarification. F prime of x minus 1 cancels out with f prime of x minus 1. We are left with 1 over x plus f prime of x minus 1 divided by f prime, just f of x minus 1. Now this is very interesting. If we make another substitution here for f prime of x divided by f of x, and we denote that to be t of x, the recursion becomes something really interesting. It becomes t of x equals 1 of x plus t of x minus 1. And if you can unroll this recurrence a bit further, t of x minus 1, its first term should just be 1 over x minus 1. And then the second term would be t of x minus 2. And then that would unroll to the first term being 1 of x minus 2. So we get an infinite, or not an infinite, but a long sum from x all the way till the subtracting value is x minus 1, because we can't do division by 0, so it can be 1 over x minus x. But we can denote that to be t0, because that's the base case of the recursion. And let's write that. Let's write the xth harmonic number to be the sequence denoted from t of x all the way till t of 1. This sequence here is just the harmonic number, or the harmonic series. So unrolling the recursion shows us that we actually find the harmonic numbers, and that perfectly describes the recurrence for t of x here. It's the xth harmonic number. But we still need to find t of 0, because that's the base case of this whole recursion. And we know we can't just plug in the 0th harmonic number, because, well, that interpretation doesn't exist. So how do we find this t of 0? That's the whole, the base case of the recursion. What we can do is we can rewrite this equation in terms of t of 0. So if we move t of 0 to the LHS and t of x to the RHS, we would get, subtract t of 0 from both sides, subtract t of x from both sides. We get negative t of 0 is equal to hx. Hx minus t of x. So how can we define t of x to gain more information, to know what t of 0 would be? Well, let's look back at what t of x really is. It's just the quotient f prime of x and f of x, f prime of x divided by f of x. If you note a bit deeper into this equation, this is equal to the derivative of ln of f of x if you apply the chain rule to d of ln of f of x of d of x. So let me write that down here. F prime of x divided by f of x is equal to ln, or d of ln of f of x, and one more bracket should be correct, yeah, divided by dx, or d ln of f of x of dx. Because if you apply the chain rule, it's 1 over f of x times f prime of x, which is exactly the quotient. And since f of x is x factorial, we're getting d ln of x factorial as t of x. But how can we, resolve that even further? Because it already has x factorial. But as we know that this limit holds as n tends to infinity, we can use Stirling's approximation for ln of x factorial, because the rate of change wouldn't be different from the actual x factorial function, as they both tend to the same behavior asymptotically. But we can say ln of x factorial is approximated by x ln of x minus x. As x tends to infinity. This is their equivalent asymptotically as x tends to infinity. So for a large sequence, we can just find the derivative of this function, x ln x minus x, which is the approximation of x factorial. And this actually works out to ln of x, which means the derivative of ln of x factorial tends to ln of x as x tends to infinity, or they're asymptotically similar or behave equivalently. So if we use t of x to be ln of x, that's the original function. So now how does that help us find t of 0? Well, let's plug in the derivative of ln of f of x factorial back into the RHS, which was approximately ln of x. So for large x, they're equivalent, and so we'll denote them to be the same to find the limit for the constant t0. And this is actually makes our job much easier, because since we have hx minus ln of x, that would denote negative t of 0, we can simply find the limit of h of x minus ln of x as x tends to infinity. And that's a known result. This is a known result. So let's write it in terms of limits now. Limit n to infinity, h of n, I don't know why I added a subscript there, or an underscore, minus ln of n. This is equal to the Euler-Mascheroni constant. It's denoted with this symbol. It's approximately 0.5772156444. I apologize, I was looking up the value for that on the internet. But yeah, so this limit, as x is large, t of 0 tends to the Euler-Mascheroni constant. And now that we have the value of t0, we can complete our equation using the original linear relation we had derived, even before this, right here. T of x is h of x plus t0. We know t0 is the negative sign version of the Euler-Mascheroni constant. So t of x is equal to h of x, which is the xth harmonic number, which grows, it would seem, a bit faster than the natural log of x, seeming that their difference yields a constant. But now that t0 we know is to be negative, the negative magnets or negative sign version of the Euler Mascheroni constant. And t of x is just f prime of x divided by f of x. And we know now that this is equal to the xth harmonic number minus the Euler Mascheroni constant, which actually shows that the true derivative of ln of x factorial is just equal to the xth harmonic number minus the Euler Mascheroni constant. But that also, not only do we now know ln of x factorial dx, since we can just multiply both sides by f of x, we also simply find d of x factorial dx. We can replace f of x to be x factorial times the xth harmonic number minus the Euler Mascheroni constant. This is the derivative of x factorial. And this corresponds to the real extension of the factorial function, because the value that you see on the RHS corresponds to the integer values of the true derivative of the factorial function given by gamma of x times digamma of x plus 1. So we, using this limit for the Euler Mascheroni constant, have found the derivative of the factorial function using its recursive properties and the fundamental limit of calculus. And we did not use the gamma function over here, although its real extension does correspond to the derivative of the gamma function, but we did not use the gamma function for this result. Thank you for watching. Bye-bye.